Let's take a look at quantity to quantity examples. These are the longest types of stoichiometry questions. There will be 3 steps involved, not just 2. All right, so let's remind ourselves first about what we need to do when we get a stoichiometry question. First things first, you need a balanced chemical reaction. Then you identify what you know, identify what you're trying to find out about. Then map your conversions, do your conversions, check your significant figures, check your units. All right, make sure you've got your periodic table and a calculator handy to do molar mass conversions, because there's quite a few of them. And these questions, when you're doing a stoichiometry question, you don't need to show your work for the molar mass conversion. If you just do the proper work on your calculator, it's good. So we have 3 more examples of quantity to quantity conversions. So first thing, tin 2 fluoride, SnF2, is used in some toothpastes. It's made by the following reactions. Take tin and add 2 hydrofluoric acids to get tin 2 fluoride and hydrogen gas. So how many grams of SnF2 are produced from the reaction of 30 grams of hydrofluoric acid with tin? So we have lots of tin, enough tin to do the whole reaction. We've got 30.00 grams of hydrofluoric acid. How many grams of SnF2 are there? All right, so first, balanced chemical reaction. It's 1, 2, 1, 2, 1, 1. That's balanced. Step 2, identify what we know. We know our HF. HF is 30.00 grams. That's what we know. What are we trying to find out about? We're trying to find out about our SnF2 and how many grams it has. So now we're going to map this. So what do we know to start with? We know our mass of HF is 30.00 grams, 4 significant figures. From our mass of hydrofluoric acid, we can go to our moles of hydrofluoric acid using our molar mass. Then from our moles of hydrofluoric acid, then we can use our molar ratio here, 2 to 1, to get to our moles of SnF2. This is our molar ratio. And our molar ratio is 2 moles of HF, 2 moles of HF for every 1 mole of SnF2. That's our molar ratio. It's 2 to 1. Then we can go from our moles of SnF2 to our mass of SnF2. Again, using our molar mass. There's our map. We're going to do those 3 steps. Right? Then I like to do the math right by the steps. So I write out how many moles are there in 30.00 grams of HF if 1 mole has, well, I need to find my mole of HF. F is 18.998, and I add to that 1 hydrogen, 1.008, get a total of 20.006 grams. 20.006 grams. Then I do 30 times 1 divided by the 20.006. And I get 1.49955. 1.49955 moles. Now this guy has 4 sig figs, 4, 5, infinite. So this guy should still have 4 significant figures. Just going to write that down there. I write down more and I keep more in my calculation. At least 1 more significant figure than my final answer should have. Now I go from moles HF to moles SnF2. So I'm going to write out my conversion. How many moles of SnF2, should be a small n, are there if I have 1.49955 moles of HF? If, from the chemical reaction, there's 1 mole of SNF2, again should be small, for every 2 moles of HF. Right, that's just my molar ratio from my chemical reaction. So I do 1.4955 times 1 divided by 2, which is the 1.4995013 divided by 2. You keep these numbers in your calculator. Keep the answers in your calculator as you go. It'll help the calculations along. 0.7497757 moles. Again, this should have 4 significant figures. And now we do our last step, and you can see it's our molar mass. How many grams of SNF2 are in 0.7497757 moles? If there are, now I need to go to my periodic table and get tin 2 fluoride. Now my calculator has this number in memory, so I can use it again. So I can do my tin 2 fluoride. SN, where is it? 118.71 plus fluoride times 2, 18.998. 137. There's 137.708 grams in 1 mole. So I just do this times this divided by that, and I get my answer. Times, and I get a total of 103.250. Now, this should have 4 significant figures, right? 4, 4, 4, 4. This one has 5, so 4 is our number. In division and multiplication questions, we keep the lowest amount. So my final answer should be 103.3 grams. 4 significant figures. There, that's all the work. That's all the steps. Until we get to limiting reagents, this is the most complicated stoichiometry problem you can find. You can see it's 1, 2, 3 steps, 3 conversions. If you write these with a little bit shorter hand, you can make sure you can do them quicker. If you want to show me that you know what you're doing, you write everything out. And I hope this is easy to follow the way it looks. Right, next one. Laughing gas, nitrous oxide, N2O, is used as an anesthetic in dentistry. It is produced by the following reaction. So we take NH4NO3 solid, and it decomposes to N2O gas and to H2O. And you can see this guy here is balanced 1, 1, 2. How many grams of NH4NO3 are required to produce 33.0 grams of N2O? How many molecules of water are produced in this reaction? Okay, so we've got 2 things. I don't have space to do both of them here. So we'll try. We'll see what goes on. So what do I know? I know I've got 33.0 grams of this, 3 sig figs. I'm trying to figure out the grams of this and the particles of this. So let's start off with the grams first. I'm going to make my map. I know my mass of N2O. From that I can go to my moles of N2O. Sorry, my mass of N2O is 33.0 grams. Then I can go to my moles of NH4NO3. Then I can go to my mass of NH4NO3. So that's my map. Let's start off with the first conversion. How many moles N2O are there in 33.0 grams? If 1 mole has, well, we got to do N2O. And where's N? 14.007 plus 15.998. 999 times 2, 46.005. So it's going to be 33 times 1 divided by that. So it's just 33 divided by 46.005. And this has 3 sig figs, so I should have 3. So I'm going to keep 4 right here in my answer, 7173 moles. But I keep my whole number in my calculator for use later. Now, my molar ratio here is 1 to 1. 1 to 1. So I know that this is just going to be the same number of moles. 0.7173 moles of ammonium nitrate. Now I can do my conversion, my last conversion. So how many grams are in 0.7173 moles of this NH4NO3 if, now again I have to do my molar mass for NH4NO3. So there's N, 14.007, times 2, plus H is 1.008 times 4, plus O times 3, 15.999 times 3 is equal to 80.043. If there are 80.043 grams in 1 mole. Do that 80.043 times that. And because I have that number memorized in my calculator, I can just hit equals, and I get 57.4 grams to the correct number of sig figs. All right. Now let's do the water one. We'll map out the water one. So how many particles of water? So again, we start out with our mass of N2O, and that's 33.0 grams. Then we go to our moles of N2O, and again, we know that's 0.7173 moles. And I've got that number memorized in my calculator, so I can just pull it up, the precise amount. Then we're going to go to our moles of H2O. Using our molar ratio. Our molar ratio is 1 mole of this to 2 moles of water. So every 1 mole of this will give us 2 moles of water. Then we're going to go to our mass of H2O. Using our molar mass. All right, so we're at this step right here. So I'm going to write it out. This one is simple enough that you can just do without writing out. How many moles of H2O are there? If I have 0.7173 moles of N2O, if there's 2 moles of H2O, for every 1 mole of N2O. So I just do that number times 2. Oh boy, something really happened here. Okay, so on my calculator, I've still got that 0.7173. Then I just click times 2, and I get 1.434. And I keep more than one I keep one extra significant figure, right? 3 here, moving on down. Now I just have to do my molar mass. So how many grams of H2O are in 1.434 moles if H2O is 15.999 plus 1.008 plus 1.008. If there's 18.015 grams in 1 mole, then I times that by 1.434. And I should do the most precise number I can, which I still have a number memorized in my calculator, 25.8. Oh, for Pete's sake. I wanted the particles, not the mass. Ugh. Well, what would I do? What would I change this to? Change this from mass, nope, to particles. I'd essentially just swap this guy with 6.02 times 10 to the 23, and I do 6.02 times 10 to the 23. And I times that by 1.4, by my 1.431. .434. And I get 8.64 times 10 to the 23 particles. 8.64 times 10 to the 23 particles. And as you can see, because I had shown all my work, it was pretty easy to fix my mistake. I just needed to change that number to that number to instead going from mass to particles. Simple stuff. Right, so map it out. Next one. Inflatable airbags contain the chemical sodium azide, NaN3. In a collision, a motor sensor sets off a spark that causes the sodium azide to decompose explosively. The products are sodium, metal, and nitrogen gas. In a typical airbag, there's 125 grams of NaN3. How many liters of N2 should be produced at STP? If a small airbag contains 50 grams of NaN3, how many molecules of N2 should be produced at STP? We're only really going to do this one here. This molecules one. The process is always the same, right? First step, chemical formula. NaN3 yields sodium, metal, that's just Na, plus N2, because nitrogen is a, diatomic. Balance this guy. Nas are balanced. N's, we got to get to 6, so 3 here, so 2 here, so 2 here, 2, 2, 3. What do we know? We know we've got 125 grams of this. What are we trying to figure out? How many liters of this at STP? This has 3 significant figures, so let's map this out. We know our mole mass of NaN3 is 125 grams. Then we go to our moles of NaN3. Then we can go through our molar ratio to moles of N2, and then we can go through our 22.4 to get to our liters volume of N2 at STP. So right, this is molar mass, this is 22.4, this is our molar ratio. Our molar ratio is we have 2 moles of NaN3 for every 3 moles of N2. So it's 2 to 3 like that. First one. How many moles of NaN3 are there in 125 grams? If 1 mole has, now I need NaN3 in here, so 22.990 plus N3 is 14.007 times 3, 65.011. So I take my 125, 125 times it by 1 divided by my 65.011, 1.998. Sorry, 1.9228. Ugh. And I keep at least one more than I need for my significant figures, but I keep them all in my calculator, and then it's pretty easy. Now we do our next question. How many moles of N2? So I'm not using green because I've already used green here. how many moles of N2 will there be with 1.9228 moles of NaN3 if there are 3 moles of N2 for every 2 moles of NaN3? So do 1.9228 times 3 divided by 2. So I take my answer, which is just my calculator, times it by 3 is equal to 5.7682546 divided by 2, 2.88. 2.884 moles. And I keep at least one more figure than my number of sig figs up here. But I have my whole number in my calculator. Last part of this question. How many liters are there in 2.884 moles if there's normally 22.4 liters at STP in 1 mole? So I take my answer, times it by 22.4. 64.6 liters of gas at STP. Of course, this gas will not be at STP because it's going to fill up an airbag and it's going to have much higher pressure in that airbag. So your airbag won't be 64.6 liters in size. All right, so the second part is just a very similar question. I mean, there's no need to really go over it. If you can do this question, you can do that question. It's more important that you get onto the homework and you start practicing these on your own. Right? They make sense when I'm doing them, but can you do it on your own? Can you go through those steps? All right, so thank you for watching. If you have any questions, please ask.